obnoxious, Bennett. You should stop. Just kidding. We're gonna review redox because we were all really bad at that. And so you should have this packet. I did attach it to the file. You can print it out on your own. Let's talk about some general definitions first. What the heck is reduction? And the way to remember this is Leo the lion says grr that you see up here at the top of your paper. Oh dear. There we go. Okay? So reduction is this part of this. It's grr. It's the gain of electrons. And what we remember about electrons is that they have a negative charge, right? Electrons have a negative charge. A substance that gets reduced or gains negatives is also known as the oxidizing agent, right? It's a secret spy name. So if they ask you who the oxidizing agent is, you want the substance that's getting reduced, okay? And the way you're going to know that something's gaining electrons or getting reduced is its charge is going to decrease because it's gaining negatives. That's the hardest part for kids to understand. The charge goes down when you gain things. What? Because you're gaining negatives. So the charge decreases. So if your charge moves down, I drew a number line here for you. If your charge moves down the number line, the substance is getting reduced. And if it's getting reduced, it's gaining electrons. Okay? Very important. One of the main, obviously, it's the name of the unit, the main concept of the section. Oxidation is Leo. Leo the lion says grr. And Leo stands for lose electrons oxidation. Oxidation is the loss of electrons. Since it is World Cup season, maybe we should say, instead of Leo, we should say Olé, right? Oxidation, lose electrons, because that's one of their cheers for those of you that are not soccer fans. A substance that gets oxidized is also known as the reducing agent. And how are you going to tell if something's losing electrons, losing negatives? You're going to look at its charge, and you're looking for the charge to increase, to go up. But you're losing things. Yes, you're losing negatives. Okay? So if you're moving up the number line, then you are getting oxidized. And you are losing electrons. I agree. Annoying. Squeaky, squeaky bench back there. Okay. So we can separate the loser from the gainer and put them in half cells. And we would call one a reduction half cell and an oxidation half cell. And if we do that, then the substance that wants the electrons actually kind of pulls the electrons through a wire. Okay? So if we separate the substance being oxidized, we kind of draw the picture like this, from the substance being reduced, we can create a battery, an electrochemical cell, okay, which contains a wire. This thing's the wire, okay, and electrons will move through the wire from the loser to the gainer. The guy that's getting reduced actually kind of attracts them and pulls them through the wire. Okay. If this is all we have, our battery won't work very well, so all electrochemical cells require a salt bridge to keep the cells neutral, and we'll talk more about that just a minute. But this is the idea. These pieces of metal that I drew here, these are electrodes. They are just solid pieces of metal. That's what they are. Okay, so if you create this electrochemical cell, electrons will flow through the wire from the substance that's oxidized, right, because he's the loser. So I'm saying from the substance that's losing electrons to the substance that's reduced, that's gaining electrons. And again, that makes complete logical sense, that they go from the loser to the gainer. It wouldn't make sense if anything went from the gainer to the loser. That's an oxymoron. It can't happen, right? If I give you money, money flows from me who's losing it to you who's gaining it, not the reverse, right? So electrons will always flow from the loser to the gainer, from who's oxidized to who's reduced, from O to R in alphabetical order, okay? The electrode, the solid piece of metal right here on our picture where oxidation occurs is known as the, does anybody know? What is the name of the anode where oh shoot. Never mind. What is the name of the electrode where oxidation occurs? It's the anode. Okay? And in a voltaic cell, which is a battery, the anode is negative. Okay? And we have a couple little mnemonics to help us remember this. So this electrode where oxidation occurs, that is known as the anode. And just like an anion is negative, the anode is negative. It is the source of electrons. Okay? The electrode where reduction occurs, anybody know that one? I'll try not to give it away. Cathode, good. And cathode sounds a lot like cation, plus cathode has the T for plus in it. In a voltaic cell or a battery, that's positive. So this electrode over here where reduction is occurring, we would call that the cathode. And in this cell, that would be positive. Okay? It's receiving electrons. It's attracting the electrons. Okay? The little way to remember this is anox, red cat. The anode is the site of oxidation. Reduction occurs at the cathode. Anox, red cat. I find myself saying that a lot in this unit. And Josh Riley came up with the VAN thing. I don't know if he came up with it. He said he did. Or if he saw it somewhere. But VAN stands for voltaic. Anode. Negative. And if you know that, you kind of know the other thing, right? You know that voltaic, cathode, positive. Okay? Voltaic, anode, negative. Electrons always flow in alphabetical order from the loser to the gainer. We already said from oxidized to reduced. Another way to say it is from anode to cathode. Good. Let's switch colors. You have to know some of the differences about voltaic and electrolytic cells. So a voltaic cell, chemical energy is converted into electricity or electrical energy. Right? This is a battery. The reaction that occurs in a voltaic cell occurs spontaneously, meaning you don't have to put any energy in, it just happens. Like if your cell phone's not plugged in right now, you're running off a voltaic cell. There's a chemical reaction happening inside here that is producing electrical energy that you're using to power your cell phone. In an electrolytic cell, it's opposite. Those two are opposite of each other in that electrical energy from a power source. So you need to plug it in, or you need a battery to make a reaction happen. It's needed to produce a non-spontaneous chemical reaction. So that's like when you recharge your phone. You use a power source to make a chemical reaction happen that normally wouldn't. Okay? So in an electrolytic cell, electrical energy is converted into chemical energy. Another difference between an electrolytic is that it's not VAN. Okay? In an electrolytic cell, the anode is positive. Okay? So it's E, right? It's electrolytic, anode positive. It's E. And the cathode is negative. It's exactly opposite. The signs are opposite. But electrons still flow from anode to cathode. That doesn't change. Okay? Oxidation still occurs at the anode. Reduction still occurs at the cathode. The only difference is the sign of those. Okay? So the salt bridge, I said we'd get back to it later. It allows ions to move. to keep the cells neutral. Okay? So if we go back up to that picture for just a moment, if we can make sense of that picture. Our negative ions are flowing, I think I was right there. Our negative electrons are moving in the wire, so we would have positive ions moving in the salt bridge in the same way. And we would have negative ions moving in the salt bridge opposite the way electrons are traveling, just to keep the cells neutral. Okay? So the salt bridge allows ions to move, the wire allows electrons to move. Any questions so far, guys? Just going to give you a bunch of information, then we're going to try some practice problems. And you at home can do the same. You just got to get the practice problems from me. A really easy way to identify a redox reaction is to, make sure the charges are changing. And in a single replacement reaction, the charges are always changing. Single replacement reactions are always redox. I'll give you an example of one. Let's say we had magnesium plus HCl. Okay? We're going to learn in just a minute the rules for assigning charges, but any element by itself is always 0. Okay? Since magnesium is higher than hydrogen on table J, it can displace the hydrogen or kick it out of the compound. And then magnesium would be with the chlorine, and due to their charges, to make a neutral compound, you need 2 chlorines. And hydrogen is all by itself. When magnesium, who's in group 2, is in a compound, it's +2. So you can see here that magnesium, its charge is going up, it's getting oxidized. And hydrogen in the compound's +1, and by itself, it's 0. Hydrogen's getting reduced, okay? So single replacement reactions will always be redox because you have somebody by themselves and then in a compound. So by themselves it's 0, in a compound it has a charge. Double replacement reactions, the wife swappers, they are never redox, okay? So you may get a question that says, which of the following is a redox equation? Look for the single replacement. If you don't see one, then you're going to have to assign charges to see whose charges are changing. All right? The important table other than the periodic table for this unit is table J. You need to know how to read table J, as in Jesse. So the metal higher on table J will always get oxidized or lose electrons. And it'll be able to kick a lower metal out of a compound, like I gave you up here. Magnesium's higher on table J, so it can kick hydrogen out of the compound. This will occur spontaneously in a voltaic cell and produce energy, okay? But a lower metal can't. Like hydrogen could never kick magnesium out of a compound because it's lower, right? It's less active, less attractive. Think of it like that. Can't kick it out of the relationship. All right, the non-metal higher on table J is more likely to get reduced. The non-metal, because there's 2 columns on table J, a metal and a non-metal column. And again, it's more active, and it will be able to kick out a lower non-metal. So for example, if we look at table J, fluorine, hi, come on in guys. Fluorine can kick out chlorine out of a compound because fluorine's higher on the nonmetal side, a more active nonmetal than chlorine is. So fluorine can spontaneously kick out chlorine to produce NaF and Cl2, but never the reverse, and we would have to balance like that. But so higher solos can kick out lowers on both sides, but not the opposite. Okay? I know there were a lot of questions when we did our test about what reaction occurs spontaneously, right? You want the solo guy to be higher. That's when it occurs spontaneously. If the solo guy is higher, it will happen. If the solo guy is lower, it won't. Okay? All right, now as the redox reaction proceeds, if we go back up to that picture, I don't know if it's, I'll just redraw it. I think it might be better. So let's just kind of draw our half cells again. Okay? If we take a look here, remember this was oxidation, this is reduction. It's not always like that. Most of the time it is. You'll have to figure it out. They'll give you a reaction to figure out who's oxidized, who's reduced. But in the oxidation half cell, the solid metal, the metal that's a solid, turns into the metal ions by losing electrons. Okay? And so as a result, this guy's mass is going to go down because he's turning into ions. Okay, we're in the redox. Keep going. Yeah, we're in redox. So the metal anode, right, which this was, the anode, because the anode is the site of oxidation, okay? The metal anode will get oxidized, meaning it will lose electrons, and it will decrease in mass because electrons are lost, and solid metal atoms turn into metal ions in solution. Okay? They ask that question a lot. Explain why metal S, this metal's mass decreases. Explain in terms of particles why this metal's mass decreases. Because this metal is getting oxidized and turning into metal ion, losing electrons and turning into metal ions. Okay? At the cathode, the opposite's happening. At the cathode, the metal ion, the metal in solution, I'm going to have to draw it down here. So at the cathode, reduction's occurring, meaning somebody's gaining electrons. So the metal ion is gaining an electron and turning into solid metal. So at the cathode, mass will increase because metal ions gain electrons and turn into metal atoms, a solid. Remember, redox reactions are always balanced with respect to mass, charge, and energy. So you got to make what's on the left equal what's on the right in terms of charge and mass. You won't have to worry about balancing energy. And when we write half reactions, for an oxidation half reaction, charge increases and electrons are a product because they're lost. But for a reduction half reaction, charge will decrease and electrons are a reactant. And like I said, we're going to try some practice problems with this. So the way we are going to identify who's oxidized, who's reduced, who's the anode, who's the cathode, which way electrons are flowing, all of this stuff starts with assigning charges. And so you absolutely must memorize the rules to assign charges, okay? And I wrote the rules out here for you. I call them rule 0 because it's kind of nice to call it rule 0 because then the first 3 are easy. If it's rule 0, any element that's by itself, not in a compound, always has a charge of 0. Rule 1, all group 1 metals and compounds have charges of +1. There's no exceptions to that. Rule 2, all group 2 metals and compounds have a charge of +2. Rule 3, fluorine in compounds always has a charge of -1 because it has the higher electronegativity of all the elements on the periodic table. Rule 4, hydrogen's almost always going to be +1. Unless it's in a binary compound with the group 1 or group 2 metal, then it's -1. Like, for example, LiH, lithium hydride. Lithium is in group 1. In compounds, it has to be +1. So that means H is going to have to be -1 because all compounds are neutral, right? That's kind of another really important thing. All compounds are neutral. So that means their charges of all the atoms have to add up to 0. Almost done. Okay? And then O is usually -2 unless it's in a binary compound with F. So if you had like OF, all right, O can't be -2 here because we know F is -1. So to make this equal 0, what's O have to be? +1, right? And if you add OF2 and F is -1, then O has to be +2. Because you have 2 things that are each -1 for a total of -2, so this guy would have to be +2. okay? Or sometimes, if it's in a binary compound with a group 1 or group 2 metal, it could be -1. You have to calculate it to see. And what I mean by that one, and then we'll get to some practice questions with redox. What I mean by that is if you have Na2O2, this is in group 1, so he has to be +1, and there's 2 of them, right? So if you calculate x, 2 times 1 is 2, 2 times x, 2x, that all has to equal 0. So subtract 2 from both sides, you get 2x equals -2, and then divide both sides by 2, and x is going to equal -1. So the oxidation state of oxygen there is -1, not -2. But you could also have this compound. And sodium's +1, there's 2 of them, and oxygen here, there's only 1 of this time. So bottom times top 2, bottom times top plus x has to equal 0. This time, x would have the normal oxidation state for oxygen, -2. Okay? So just because it's in a binary compound with a group 1 metal doesn't necessarily mean it's going to be -1. You should calculate it to see what you need to make them equal 0. This is an example of what we call peroxide. When oxygen has the -1 charge, it's actually a polyatomic peroxide. Oxidation state is always given per element. It is never the total, okay? So, for example, here, if you were to ask the oxidation state of sodium, you would say +1, not +2. It's the charge on an individual sodium atom, not the total due to sodium. Okay? That's redox in a nutshell. That's the whole unit. I can't think of anything else that we haven't covered. So I think now we'll leave you, for all of you at home, and we're going to do some practice questions. Make sure you go do your extra credit CASA writings. Bye-bye, everybody. Okay, guys, so let's go to